Hello everyone, and this will be a quick demonstration of what the pair production, pair annihilation, and the Heisenberg uncertainty principle is. So let's start off with Heisenberg's uncertainty principle. So what he basically said is that, let's just state the formula here first. There's two different forms, which I will explain to you later. First form is this one right here. So the change, or the uncertainty in position times by uncertainty in momentum, it has to be greater than h, which we know the Planck's constant, which is a ridiculously small number, over 4 pi. So essentially both of these right here, this momentum and position, they are conjugate variables, right? They depend on each other. Right here, to the energy of the particles times by the time that it exists for. It's the same concept. So essentially we can picture this as a pool ball, right? These are the snapshots or the time frames. We could figure this as two ways. First of all, we could have a high resolution camera. Second one would be a low resolution video recorder, right? So if we have the high resolution camera, then we would exactly know the position x. We would know exactly where it is, but we would not know the momentum. We do not know the mass, and we do not know the velocity. Sorry, we know the mass, but we do not know the velocity, the distance over time, right? If we have a high resolution camera, we won't know that. But contrastingly, if we have a low resolution recorder or video recorder, right, we would know the velocity because of the speed and the time, or the distance and the time, right? Sorry, the distance and the time through the length of the recording, right, and the distance that it travels. There's a trade-off between position and momentum. Similarly, there's also a trade-off between higher energy and the time it exists for. So the higher energy of the particles, the less time it exists for. See, it's not possible to measure simultaneously the position and the momentum of particles with indefinite precision, right? You have to choose one of them. So how does this link to annihilation and pair production? So let's give an example of pair production right here. Let's see, this is a photon right here. If it decays into an electron with a mass and an electron without mass, we can see that mass and the energy is conserved due to pair creation, right? Mass is turned to energy. The lepton number is also conserved, but the momentum is not conserved in this particular case, because right here, the initial momentum, it's a value, it's a non-zero value, but here, these two together, the momentum after it, since they go in different directions, right? This is a Feynman diagram. Since they go in different directions, the momentum after is zero. So there has to be a nucleus, or there has to be some sort of body to take some of the momentum away. So the nucleus is that particular body. See, when both of them collide, it's known as the term annihilation, and it's exactly opposite of what I have just explained. So two electron and a positron, which is the anti-electron. This is the wrong direction. Electron and a positron. I got E here and a positron. When they give out a photon, mass is turned to energy, lepton number is conserved, but momentum is not conserved. When they collide with each other, they collide at very high energies. See, there's a trade-off between the energy, because we know that mc squared equals 0.55 something, and two of them would equals 1.02 MeV. It's in the data booklet. Right, what's the significance of this? So during the lifetime of the electron-positron pair, there is an uncertainty regarding the total energy, right, of this because of the quantum mechanics nature. But there's a trade-off. If it's a larger energy, we would see it for, or we would visualize it for, or it would exist for a shorter period of time. So if the energy is much less when it annihilates, we would see it for a longer period of time. If we cannot perform an experiment to detect a violation of the conservation law, then quantum mechanics says there is a small probability of the process occurring.